Hi everyone, in this lecture 6, we will calculate the non-equilibrium solutions of a p-n junction. In the previous lecture, we solved the nonlinear Poisson equation. How can we perform the drift-diffusion simulation? In this time, we wanted to apply a voltage to the anode. Then, how can you apply a voltage to a contact? We must introduce a voltage source. After that, two thin objects, a p-n junction and a voltage source, should be connected. Those tasks are done by these lines. The lumped type thin object is for a voltage source. By setting its value 0, we start from the zero bias condition. In order to construct a circuit, each terminal of a circuit element is connected to a circuit node. Now, let's define the drift-diffusion model. In addition to the Poisson equation, two continuity equations should be added. After adding these two equations, internal quantities such as the electrostatic potential and the carrier densities are considered in the simulation. However, we need more. We must care about the terminal currents of the p-n junction. Also, terminal currents of the voltage source are taken into account. Circuit node voltages are also needed in the circuit analysis. Therefore, the number of equations is a little bit larger than 3. Now, we are considering how to monitor the IV curve. In general, there can be a large number of terminals in a circuit, and some of them are not important to us. For example, in this case, the IV curve of the voltage source is not of our interest. Using the book statement, only selected terminal quantities can be printed. Here, CSV represents the name of the CSV file, the output file. We will consider two terminals of the p-n junction. Other quantities are not printed. Then, how can we visualize the CSV file? It can be led by many tools because it is just a text file. Of course, the ParaView also recognizes the CSV file format. Let's start the simulation. We wanted to increase the voltage. It is done by changing a quantity voltage of the voltage source. Unfortunately, we cannot abruptly change the voltage from 0 to its final value. Instead of that, we'll ramp up the voltage. This procedure is controlled by parameters such as initial step, mean step, and max step. When the simulation is finished, the alpha file dc.cgns represents a device biased at 0.7 volt. The fold IV curves when the voltage is changed from 0 volt to 0.7 volt are shown below. These curves show the identical data with different y-axis settings. The left one is shown in the linear scale and the right one in the semi-logarithmic scale. Its exponential dependence on the applied voltage is clearly observed. You know an analytic expression for the diode current. Try to calculate the current using that analytic expression and compare the result. In the semi-logarithmic graphs, you can estimate the slope. Check that the slope is 60 millivolt per decade. It was a forward sweep in the previous slide. Now ramp down the voltage to minus 0.7 volt. It is easily done by changing the goal value in the input file. Then the output curve looks like this. At minus 0.7 volt, almost no current. On the other hand, at 0.7 volt, the anode current was about 4 times 10 to the minus 7 ampere. More than 11 orders of magnitude difference is observed. Of course, such a behavior is related with internal quantities. As an example, the electrostatic potential is drawn at 0 volt and 0.7 volt. Since the applied voltage difference is 0.7 volt, the electrostatic potential at the left contact, the anode, is changed by 0.7 volt. Since the change of the electrostatic potential is directly related with the energy barrier, we can understand that the energy barrier felt by electron at 0.7 is much lower than that at the equilibrium case. That's the reason why we have a large current. That's it for this lecture 6. Now we can perform the drift diffusion simulation. Moreover, we can draw the IV curve and see the internal quantities. Great! However, up to now, we have not thought about the physical models inside the semiconductor device. In the next lecture, we will discuss the physical models. Thank you and see you later.